everybody. Last time we were talking about solution concentrations, and we were looking at qualitative versus quantitative concentrations. Qualitative, if you remember, is the diluteness, so whether solutions are dilute or concentrated. Quantitative, we talked about molarity and using the molarity to calculate two things, to calculate dilutions, so how to make solutions more or less concentrated, more dilute, and looking at acid-base titrations, which was the same formula, but for acids and bases. So how to make an acid more basic or base more acidic to kind of pull them more toward a neutralization point. We're going to talk about two more quantitative concentrations today. Remember, this is all in the realm of solutions, so solutes being dissolved in solvents. That's kind of the overarching theme of this unit, so solutions in general. So the first concentration we're going to talk about is percent by mass. This is going to look awfully similar to percent composition that we saw a few units back. The percent by mass is the mass of a solute divided by the mass of the solution times 100. So when we saw this for percent composition, it was the mass of one atom or element divided by the mass of the total compound times 100. Here we have solute and solution. And a sample problem is going to look like this. What is the percent by mass of an NaCl solution containing 17.5 grams of NaCl per 500 grams of water? So if we're looking at this, we need to figure out where's the solute here and where's the solution. So we have an NaCl solution. That means it's made up of NaCl and water. So our solute here is the NaCl. That NaCl is dissolving in the water. So water here is the solvent. Solute, solvent, and together they make the solution. So for our percent by mass calculation, we have mass of solute over mass of solution. So our mass of solute is given to us right here, 17.5 grams. So we have 17.5 grams of NaCl divided by the mass of the solution. Well, remember, here's our solvent, here's our solute, together they make the solution. So the mass of our solution is actually 17.5 grams plus 500 grams. That's our total solution. So 17.5 grams divided by 517.5 grams times 100 to get it into a percent, you get a percent by mass of 3.38%. Okay, so this is 3.38% NaCl, the solution. The second concentration we're going to talk about, I'm going to move the board one more time, is molality. Remember we saw molarity with an R. This is molality with an L. This is going to be used to calculate a couple things at the end of this video as well. Molality is abbreviated with a small m, not to be confused with mass or meters. Also not to be confused with molarity, which was a big M. This is molality, little m, okay? Molality is still moles of solute, just like molarity was, moles of solute on top. But in the denominator, we have kilograms of solvent, okay? So we have to have kilograms of solvent. The solvent here for our solutions is water, most often. Okay, so sample problem, calculate the molality of a solution containing 50 grams of NaCl dissolved in 3 kilograms of water, right? Well, we know on top that we need moles of solute, and fortunately, we all already know how to get from grams of our solute, again, NaCl is our solute, how to get from grams of solute to moles of solute. We just divide by the molar mass. Grams on top, grams on bottom, 1 mole on top, and we get 0.856 moles of NaCl, okay? So here again, this is our solute. Water is our solvent, okay? Sometimes it's helpful to label those so you're not getting solute, solvent, and solution mixed up in your calculations. All right, so we have moles of our solute, which we've already calculated. That's going to go on top here, so 0.856 moles of NaCl divided by kilograms of solvent. Here it's water, 3 kilograms of H2O. And when you divide this, you get 0.285 molal. Okay, not molar, because this is not molarity. Molal, little m, because it's molality. Okay. Once you know how to calculate molality, we're going to be calculating temperature changes in boiling point and freezing point. That is what we refer to as colligative properties. So that's what we're going to be looking at now, is colligative properties. And these are properties that depend only on the number of particles dissolved. So how many particles are dissolving in solution? The number of particles we call the Van Hoff factor, and it's abbreviated with an I. When you see I, you're going to be calculating the number of ions or formula units that, that a solute will dissociate into, okay? Remember, dissociating means that it's going to break up into its ions. If you have something that's not going to break up into its ions, so non-electrolytes, they don't break up into their ions because they aren't made of ions. They're molecular solutes. If you have non-electrolytes or molecular solutes that don't dissociate, then I is going to equal 1, right, every time. There is no unit for this, it's just I equals 1. So for table sugar here, C12H22O11, I is equal to 1, because this is a molecular solute. We know it's molecular because there are no metals in it, no cations in it. It's only made of nonmetals, okay? So that is a covalent compound, molecular compound, same thing. If you have ions or formula units for electrolytes that dissociate, then I will equal the number of those ions or formula units. So up here, I is equal to 1. Down here, I will equal the number of ions or formula units. So NaCl is going to break up into Na plus and Cl minus. That's only 2 different ions. Okay, so for this, for NaCl, I would equal 2. Now this says ions or formula units, so we also have to pay attention to formula units. We don't break them up into their individual atoms, we keep the formula units together. So here we have Ca3PO4 Well, there's 3 calciums, right? If you remember the calcium ion, 2 plus charge. The PO4 phosphate, 3 minus charge. All right, but what's important here is that this is in solution. It's going to break up into the calcium ions and the phosphate ions. 3 calcium ions, 2 phosphate ions, 3 plus 2, I equals 5. Okay, so we're just counting the number of ions or formula units that the solute will break up into or dissociate into. All right. Now, what this all can be used for is looking at types of colligative properties. So there are certain colligative properties. Again, they depend on the number of particles dissolved. The most common ones that we talk about are vapor pressure lowering, where the vapor pressure of the solution will be less than the vapor pressure of water, right? So then the solvent, vapor pressure of the solution would be less than the vapor pressure of the solvent. Freezing point depression, where the freezing point of the solution will be less than 0 degrees Celsius. You see that, for example, if you're making homemade ice cream, you can add rock salt to the ice, okay? And that drops the freezing point of the ice a little bit so that you can get the milk mixture that you're trying to turn into ice cream, you can get it to a lower freezing point, a lower temperature than 0 degrees Celsius. Otherwise, ice would just be at 0 degrees Celsius. So you can get it a little colder to make it really freeze into ice cream. Boiling point elevation is our third colligative property, and that means that the boiling point of the solution would be greater than 100 degrees Celsius, which, if you remember, is the boiling point of water. We see this with adding salt to water if you're trying to like boil water for pasta. This is kind of twofold because the salt does increase the boiling point of the water, but that doesn't make your water boil any faster. What makes the water boil faster is that salt in the water also decreases the heat capacity. So remember specific heat capacity we talked about? It takes less energy to heat up that water. right? So the water will ultimately boil faster. That one, for both of those, it takes a ton of salt. If you're trying to change the boiling temperature of your water, it would take way more salt than any of us would ever add to water to make that happen. But there's the idea behind the boiling point elevation with adding salt to water to make it boil. For both of these, freezing point depression and boiling point elevation, we're going to use a couple of constants, a Kf and a Kb. So this is a constant, a freezing point constant, and a boiling point constant. For freezing point, it's 1.86 degrees Celsius over molal, and Kb, our boiling point constant, is 0.52 degrees Celsius over molal. Those are going to be used in our change in freezing temperature, or change in freezing point calculation, and the same for boiling point. Kf, our constant, times molality times I, which we looked at up here. Kb times molality times I, which we have, again, I here, and the Kb down here. All right, so let's take a look at what these calculations look like. All right, now that we know how to calculate molality and we know how to find I, all we have to really do is plug that in. So for this problem, calculate the freezing point of 50 grams CaCl2, calcium chloride, dissolved in 1 kilogram of water, okay? Well, we know that we're going to need molality, so we're going to have to calculate molality here. If you notice, we have 50 grams of CaCl2, that's our solute. To calculate molality, we need moles of solute. We have grams of solute. Well, luckily, we again know how to go from grams to moles using our dimensional analysis. I've done that here for us. So we know we have 0.451 moles of CaCl2, right? On the bottom, we're going to have kilograms of solvent. Remember, the solvent is water. We have our solvent right there, 1 kilogram of water. So I'm going to plug in 1 kilogram of water, and we get 0.451 molar, right? Now we can plug that into our delta TF. This is going to calculate the change in the freezing point, okay? Ultimately, we're trying to calculate the freezing point. This is just how much that freezing point will change, okay? So our Kf, which remember for, I don't know if you can see this, the Kf, our constant, is 1.86 right here. So we plug in 1.86 degrees Celsius over molal. Plug in the molality, which we calculated to be 0.451 molal, and plug in I. Okay, well, we have CaCl2. How many ions will this dissociate to? There's 1 calcium, 2 chlorines, or chloride ions, for a total of 3, right? Multiply this out, and you get 2.52 degrees Celsius. Well, that's the change in freezing point. This is not the new freezing point. You're not going to freeze at 2.52. It's a freezing point depression. So we actually have to do one more step where we subtract that from the freezing point of water. So our new freezing point of water, or freezing point of the solution here, the CaCl2 and the water, would be negative 2.52 degrees Celsius. We can do the same calculation. I'm using the same exact data here to calculate the boiling point of 50 grams of CaCl2 dissolved in the same amount of water, right? Now I put here, note the same measurements as above. So the molality is the same, right? We still have 50 grams of CaCl2, therefore 0.451 moles. We still get the same molality, okay? So there's our molality. We can just go ahead and plug that right into the equation for molality, right? This time we're using the Kb, right? Not 1.86, because that's our freezing point constant. We're using 0.52. That's our boiling point constant, degrees Celsius over molal. And then our I here, same as above, because we still have CaCl2, and we get 0.704 degrees Celsius. This time we're not subtracting it from 0. This is boiling point elevation. So we're adding it to 100. And our new boiling point of the whole solution is 100.704. And that would be our new boiling point.